Hello world, Joshua here. I want to be teaching you about how to solve this problem, binary tree maximum path sum. Alright, we're tackling finally a big boy, hard, or big girl, to be gender neutral. Actually, you know what? I'll retract that statement. I don't want to exclude anyone else. Because given a non-empty binary tree, find the maximum path sum. For this problem, a path is defined as any sequence of nodes from some starting node to any node in the tree along the parent-child connections. The path must contain at least one node and does not need to go through the root. Alrighty then. Okay. So let's look at some of the examples. Oh, by the way, before I actually start solving this, I'll include the problem description, the link to this LEETCODE problem in the description below. So let's get right to it. Alright, the first example. In this case, the maximum sum will be, maximum path sum will be 6 because 2, 1, 3, they all add up to make a 6th value. Now in example 2, it's just going to be 15, 20, and 7. It'll make 42. That's because they don't want to include negative 10 and 9. It's because it will decrease that sum if we include it into that value. No hints. Wow, this is going to be so easy. So first, what is a binary tree? Tree, I could flash this funny meme. Oh gosh, darn it, there's so many memes. Let's just, but anyways, what is a binary tree? First, let's go over the concept of a tree. Let me see if we can find a good example right here. Is there a diagram? Okay, so a tree is like, there's a parent node and it has children nodes right below it. And that children node could have children right below it as well. Now, a binary tree is just like this tree right here. It's when that parent only has up to 2 nodes. It could be 1 node, it could be no nodes for each node. Now, in my case, I think I would, if I want to go find out the maximum path sum, what I need to do is, hold on for a second, guys. My apologies. I'm going to drink some water. So I'm thinking about this. There's some scenarios that I have to consider. One, the node itself could be a maximum, and the node at the right itself can be a maximum. Let's just say if, like, there's a negative value. Okay, yeah, let's just think of the possible scenarios right here, because we know that it could be at least one node. So in just, if they're all negatives except this 20 right here, then that 20 will be the maximum path sum because it could be at least one node. Let's see what else. If they're all negatives, you have to find that the least, the smallest negative number so that it will be, greater than the rest. Like, let's just say you see, like, negative 1, negative 3, and negative 5 in this whole tree. Negative 1 in itself will be the maximum path sum. So we have to consider that as well. Left, right. So let me think about how I would break this down. If I want to traverse this tree, how should I do that? Let's think about this. I'm going to think about this intuitively first before I start solving this question, so that perhaps, if you follow my train of mind, we could both agree on a solution. So let's see right here. So if I'm starting at this node, I'm giving this node right now. This is the root, and I can determine the children right to its left and to its right. So what I want to do first is I want to go gather information. Could it go left and right? Is there any other branches that extend from that root? And if so, I want to see if we could calculate the maximum path sum if that 2 in itself would be its own tree, or the 3 itself would be its own tree, and I'll kind of repeat that process. You can see that it's going to be a recursive function because, I'll be repeating that sort of idea recursively. I'm going to keep calling the idea, alright, if there's a temporary tree right here, could this by itself be its own max, create its own maximum path sum that if it were to the original root value or its parent, it would not have that value. And you can see that in this scenario right here. The root value is only going to bring that maximum path sum down. And the base condition where it will stop is if it travels to there's no, it reaches an endpoint and there are only null values right below it. Okay, so I think at least I could define that for now. So let's just type something for a second. We want to find the maximum sum. Okay. The maximum sum, for now, we're going to just put a placeholder value to be the root.val. And I'm going to create that recursive function based on starting at the root. And I want to return the maximum sum at the end. Now let's create that recursive function. Public int traverse tree node. Now the base condition. So when I do travel through each of these branches below, I have to know when to stop. And as I mentioned, I stop when it reaches an endpoint when there are only null values extending from that node. So it'll be node equals null. Okay, and now you might be asking why I made this an int. Because on the way that we travel, I'm going to say that we're going to need to know if let me think about this. I made it an int. Okay, so when we start with this, when it's this parent node right here, and we check its left and right values, we're going to need to investigate what these values at the maximum path sums at each of these branches. What will those be? That's why I made it int. So okay, first I'm going to return 0 here, because once you reach the null, it's basically there's no value to add to the temporary sum that you're creating. Now if there is a value, you want to do int left equals traverse node.left, and int right equals traverse node.right. Okay, so we get the values from the left and the right hand side when we recurse right through it. Okay, and now if the left and the right would return a negative value, do we want to add that as our maximum of the left hand side or the right hand side? No, we don't. We would just want to neglect that value. So that's why I made it a 0. So let me just explain to you my thought process right here. I'll make this a 0 right here. Sorry about that. Traverse. Okay, so here's what we do. We'll traverse to the node left, and we found out that it's going to return a negative value. Now, once I have the left and right values, and for example, the right hand also has negative values. So now I compare the maximum sum at this point right here. Maximum sum equals, now I have to decide, do I want to keep the maximum sum that I currently have, which is 0, or I mean the root value, I'm sorry, the current root value, or do I want to include the path with the left and right and node val? Now you can see this, the scenarios that I referenced earlier, like let's just say that this is negative and this is all negative. It wouldn't be useful to add it to this max sum, because it's going to only make it, it's going to bring that sum that you're going to create right here, it will bring it lower. So that's why, I had the choice. Do you want to add that the values, the maximum path sums of the left-hand side or not? And so far, let's just say the values there are negative from the left-hand side. Like, let's just say this is -2 and this is -3. And the root value is 1. Let's say -2, -3, and this is 1. We don't want to take any of the values from -2, -3, because the maximum path sum, if we include that, include those branches, it's going to be -4. So we want to exclude that. So we don't add them at all. We just basically stick with the node value that we have. Now we have the maximum sum. So now let's return. So now we have, let's just say that we found out what the maximum sum is. We finalized that one. Now what can we do then? Now there might be scenarios. We have to consider these scenarios as well. So we have the scenario that we try to see if we could add all of them at once, or let's see for a second. Let me think about this. Now I want to see if I can return the maximum max of the left and the right hand side. Oh yes, so as we traverse, we're creating that sort of temporary sum. So let's think about it right here. -10, 27, And now we're traveling from that node value like previously right here. You know, we can go right here. It'll be 20 plus 7 or 20 plus 15. We have to choose which path might give us the maximum, which is say we traverse. So what I'll be doing right here is that I want to choose the maximum value of which pathway gives me the biggest value. Is it the max of the left-hand side that will get me the bigger value, or the right-hand side? You can see right here that 15 will be the bigger number. So in that case, I'll just travel right through as plus node.val. So let's see. So let me think about this. I want to make sure my thought process is. Let me just summarize right now. So one, we initialize the maximum sum to be the root value, just as a placeholder until we could find a value bigger than that. And we create a recursive function that goes through the whole tree to find that the maximum path sum. And it will stop once it reaches once it knows that it's in the endpoint where the nodes will be null. Now the left-hand side and the right-hand side, we check both sides to see if it's actually going to bring up the maximum sum of the value. If not, we don't want to add it to what we're finding out. So let's just say this is -2, but 1 and 3 are the same. That means we just want to use the 1 and 3 itself, and this will be, we'll just return a 0 at the left-hand side. And then the maximum max sum at that point will be just right plus no.val. And compared to the maximum sum, then if you are to take this example that is said here, this is 1, 3, and this is -2, then 1 plus 3 is 4, which is bigger than the root value, which is 1, so 4 will be the new maximum sum. And now, once we've done that, we want to return the maximum sum of, oh my gosh. I can see why this question is hard. Man, let me just slow down for a second. Okay, so there'll be a bunch of traversal calls done, as we traverse this whole tree. And, returning the maximum max of the left and right plus no.val. We cannot. There's something we want to emphasize. I should have said earlier in this video. My apologies for not doing this. There's no backtracking, so I cannot do this. -10, 20, 15, 27. I can't do something like that. It has to be just one direction and no backtracking. So this is why I did return math.max of left and right plus no.val. Because when we traverse through this tree, I want to see which one will bring me the bigger value, the 15 or the 7. Because we're checking that option also. If we do one whole long path like this, would that create the maximum sum? And if not, then we just stick to whatever the maximum sum was. So this is why I'm returning the option. I want to add this note.val, and then if it's going to extend to one of these pathways right here, it's going to be one of these, the one from the left hand side or the one from the right hand side. Alright, so let's hope that this works, because I went through a long explanation, and if it doesn't work, then I'm sorry for the 20 minutes you've listened to me. Oh, I'm not sorry, because it's right! Oh, wait, actually, slow down, Joshua. Let's submit the problem. Huzzah! Okay, so this works. So I hope that this makes sense. If I were to find the time complexity and space complexity of this answer, since we'll be going through every single node, I would say it's around O of n time complexity. And the space complexity will be around let me think about this. I'm not really so good with space complexity, to be honest. But since there's a bunch of traversal calls, worst case scenario, if it's all one long line, it'll be O of n. If it's just like this, maybe it's like O of n over 2. Because, the traversal calls can only go up to, if it's a well-balanced tree like this, it will go up to O of n over 2. So, please leave in the comments below if, you can even explain better than what I did about space complexity, time complexity. About solving a problem like this. I'm afraid that's like a weak point I'm trying to improve. I would like to learn also, so please post in the comments below if there's a better way to solve this. I think there's a better way, like if you use an iterative solution, then and use a stack. I think that could be another way to solve this problem. I wasn't able to implement it myself, but you could go ahead and try if you'd like to. And that's about it, guys. Thank you for watching and for sticking me hard with this hard, this hard question. I'm gonna send you a free Bulbasaur. When you wake up the next morning, your mommy and daddy will carry you a Bulbasaur and put it on your lap, and you get to play Pokemon all day long. Just kidding, guys. Just kidding. I'm a bit exhausted today, and I'm gonna eat some food. Have a good day, guys. See ya.